Hello. Today I want to talk about dual contouring, which is a relatively common way to represent implicit surfaces as a triangular mesh, or rather to create the triangular mesh from the implicit surface. Now, if you don't know what an implicit surface is, this is one potential example. An implicit surface is a surface that can be represented as a distance to it. The easiest example is the sphere. When you have a sphere, that sphere has a radius, and so when a point is right at the surface of the sphere, the distance to that surface is 0, and then if you move a little bit away from the sphere and outside of it, you're going to have, some distance. And then as you move towards the center and you are inside of the volume described by the sphere, you are going to have a distance that is smaller than the radius. When you subtract the radius from it, you're going to have a negative inside and positive outside. Now, I am going to go into more detail in a bit, so if it's not clear now, I will make sure to be more thorough and to actually show examples. However, I just wanted to show you this particular one because I think that the surface itself is pretty cool, it's pretty neat, it's pretty beautiful. And also to show you that when you do the most naive kind of implementations like the one that I have, you can get artifacts, and how to prevent these kind of artifacts is, if I understand correctly, still an open area of research. So you can see, for example, in here I missed a little triangle, in here I missed some other triangles. You can see that there is like this rough, almost cubic aspect to it, and this all comes from some limitations of my own implementation that would need to be addressed, but it works. I've applied subdivision to the triangular mesh that was generated and my program didn't crash. So yep, it means that although there are artifacts, the representation itself is pretty robust and pretty good for many geometric elements. So let me pass to the drawing board and I will explain how dual contouring works a little bit better. Okay, so the first thing before going into dual contouring itself, we need to talk about implicit functions. Now, very generally, a implicit function is a function that can be written as f of x, y. I'm just gonna go all the way up to the z, but it could be in higher dimensions, which is equal to 0. Now, there is a slightly different way to describe them, which is instead of f of x, y, z equals to 0, which is the implicit representation, you can just extend that to be a distance function. And so it is f of x of y, z is equal to some distance. The idea is that this distance is going to be negative when you're inside the volume described by the surface, positive when you are outside the volume described by the surface, and 0 when you're exactly at the surface. So to return to the example that we were first talking about, the sphere, it's fairly simple to see how you can generalize it. So we're going to say that we have a sphere, right, and we have the center. So this is anywhere in the 3D space. It doesn't have to be at the origin, it can be anywhere. How do we know whether we're inside the sphere or not? Well, we know that the sphere has a radius, right? And if we grab any arbitrary point that is outside, then the distance from the center to that point, this line, minus the radius is going to be positive. And if the point is inside, then the distance from the center to that point is going to be negative, minus the radius. Or, if we put it mathematically, if the point minus the center, the norm of that, so this is the distance from the point to the center, minus the radius is negative, then you're inside of the sphere. If this is positive, then you're outside of the sphere. If it is exactly 0, then you are on the surface of the sphere. And it's fairly straightforward. Now, if you generalize it for other surfaces, so let's say that we have, some weird, strange implicit surface, and maybe that implicit surface has some holes in it. It doesn't really matter. It's going to be the exact same thing, except that it's not going to be the radius. The mathematical formulation is going to be more complicated than for a sphere, but the idea is the same. If I have a little point that is outside of the volume contained within the implicit surface, this should be giving me positive values. So the distance here should be positive. And if I pick a point that is inside of the volume, then the distance here has to be negative. Now, that is a very high level overview of distance fields and implicit functions. This is a topic that could take like many videos. Hopefully this high level overview is enough to convey the idea if you were not already familiar with it. But I want to move on to dual contouring. So how does dual contouring actually work? Well, the idea is we start with our implicit function. So let's say that our implicit function is describing this blob over here. The first thing that we want to do is we want to inscribe this blob inside of a grid that is large enough to contain it. So for example, if this is my grid, then this grid would be large enough to contain my blob. However, notice that this grid is a little bit too large because this corner over here is essentially wasted space, and the same thing happens with this, and the same thing happens with this. So this is good enough. This would be good enough to do an implementation. This would be good enough to inscribe the volume inside of the grid. However, it is better to try to make the bounds as tight as possible. So in this case, if you could do the grid using only these corners, it would be arguably better. The reason being that if we just use this portion, then we're not wasting space. It's not absolutely necessary, but it's something to take in mind that you want your grid to be as tight to your surface as possible. The other thing that you need to take into consideration is the level of resolution. The level of resolution is how many divisions there are on that grid. So, this I can divide like this, and that is a grid. But if I try to put, for example, a sphere inside of it, I only have 4 quote-unquote pixels or voxels to try to represent that surface. However, if I start adding more divisions, and then I add even more divisions, the amount of resolution, the amount of data that I can encode within my surface increases. The problem becomes that I am using more memory. So it's this trade-off where you want as much resolution as necessary for whichever visual application you're trying to do, but not more because you don't want to waste more resources than you need to. So that's the other thing that you need to take into account. These are going to be called the span, for how big the grid is compared to the volume, and the resolution, which is how many subdivisions you are in the grid. Now, with those two ideas in mind, let's actually run the dual contouring algorithm that has been implemented in NeverEngine. So the idea is we have 2 passes. On the first pass, we're just going to focus on which cells have points. So the idea is the following. Let's say that we have a grid, and I'm going to make a small one just because I don't want to spend too much time running the algorithm. So let's say that we go, and this is our grid. We're going to start on this cell, and we're going to ask ourselves, is any of the edges in this box crossing the boundary? how do we know if an edge is crossing the boundary? Well, an edge crosses the boundary if, when you look at its endpoints, one is negative and the other one is positive. It doesn't have to be in this order, it could be positive and negative, but what you're caring about is if the endpoints have different signs, then you are guaranteed that your surface crosses that edge. And to see why, it's very simple. If all the edges are inside of the volume, then they're all negative by definition, right? If the endpoints of an edge are both negative, that edge is fully contained inside of the volume, so it's impossible for it to be outside of it. So this is this example. In this case, both of them would be negative. If both of them are positive, then it is possible for your boundary to cross that edge. However, the other possible circumstance is that the boundary doesn't cross it. In this case, you use the heuristic that your resolution is going to be high enough that this case where the edge is larger, like the distance in between the endpoints of an edge is bigger than your volume, never happens. So unlike the other one where it is mathematically guaranteed that that case cannot occur, in this case you can have the boundary cross and have positive signs on both ends of your surface. However, you work under the assumption that your grid cells are so small that this is never going to happen. So the only case where you admit that the surface is crossing your edge is when the sign flips at both ends of the edge. And now, knowing that, what we're going to do is we're going to test this edge, 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 and in 3 dimensions we would test like all 12 edges. Now, if at least one of these obeys this criterion of the signs being different, then you are going to mark the cell as being occupied. You are going to put a vertex there. In all other circumstances, you're going to leave it empty. So if I give you an example with like an arbitrary thing that just comes out of my head, we're going to make our blob, and then we're going to try to make a grid, and we're going to encase our blob on that grid. So if we follow the algorithm in this case, so we check this one, all of the edges are outside, right? Like all of the endpoints of my edges are going to have a positive sign, so I just ignore that. Then I test this one, and same thing, I ignore it. There's nothing for me to do with that one. And then I move on to the next cell, same thing, next cell, same thing. Then I go to the next row, and then I test. So I test this one, same thing, there's nothing there. Then I test this one, and when I test that one, something is going to happen. There is at least one edge that has different signs, which is this one, right? The vertex on the right is going to be negative, but the one on the left is going to be positive. So I am going to put a vertex on this cell. And then the same thing is going to happen here. I am going to mark this, and I'm going to put a cell here. Then on the next one, I'm not going to do anything, and then I go to the next row, and then if I mark all the ones where I see that stuff crosses, I end up getting something like this, correct? And so with this, we now have all of the vertices that we actually want to connect together. Okay, so we've managed to identify the cells that should actually contribute to our surface. The next question ends up being, how do I connect these points together? Actually, sorry, I'm getting ahead of myself. The first question is, what is the best position for these vertices? Because in my diagram, I try to place them more or less on the center of each cell. But as you can see, the boundary is not necessarily passing through the center of that cell. So in an ideal world, we would be moving our vertices to try to be located as close to a point on the boundary as we can, right? So there's many different ways to do this. The way that I implemented on NeverEngine is I just do gradient descent. Essentially, to do the kind of gradient descent that I use for that demo that I showed at the beginning, I take the implicit function, and then I take the square of that, and then I take the gradient of it. And the reason for doing the square is because if you look at a distance function would look something like this, where when you're on inside of the surface, you're on this region, and when you're outside of the surface, you're on that region. But if you look at the gradient in this kind of function just moves in that direction, which is not exceptionally useful. On the other hand, if you take the square, then your function is going to look more like this. As this touches the edge, by the way. So like it here is where your surface boundary actually lies. So this position here is when you actually want to put your surface. And if you look at the gradient, now this is like a bowl. So the gradient is now actually pointing to the actual surface rather than always pointing on the same direction. So gradient descent in this case will actually try to converge towards your surface. Now, as you saw, gradient descent is not the best. It's so easy to implement the discrete gradient operator, and it's so easy to square a function, and it's so easy to do gradient descent that's what I went out doing, because I didn't want to spend too much time just making a demo. Now, once you've done gradient descent on your cells and you look back at your grid, your vertices should now be lying like relatively close to the surface. So if it was a circle, like say that our circle just crosses to all of this, and yeah, and we get that. Now the problem is that we need to connect the cells together. We need to triangulate them. Now, in order to be able to triangulate them, instead of visiting every cell, now what we're visiting is every edge on the actual grid. So if this is our grid, and I'm drawing a lot of grids today, we're not going to visit the cells. We're actually going to go, okay, so I'm going to visit this one first, then this one, then this one, and then I'm going to visit this one, and this one, and this one, then this one, so on, so on, so on. You are going to be iterating on the edges of the grid, not on the cells of the grid, and that distinction is important. You'll see why. So let's say that I am in 3D and I am looking at a vertical cross section of my grid. So we're going to assume that these circles are edges that are popping out of the screen, you know, like these little circles that I just drew. These are the edges, except that oh my god, I cannot draw. There we go. These are the edges that are orthogonal to my drawing surface. They're popping out of the screen, like something like this. So try to picture it in 3D. I am currently looking at this edge over here, the one that I am highlighting in black. Okay, so I am going to first test whether that edge crosses the boundary, and this is the same thing as before. If the endpoints have different signs, then this crosses the boundary. If this edge crosses the boundary, then I know for sure and for a fact that I have marked this cell, this cell, this cell, and this cell to be. Actually, let me use a different notation convention because this might be a little bit confusing. Okay, so I will have marked these cells. Now again, the points are not necessarily on the center of every cell. They might be spread around a little bit, but they're guaranteed to be inside of each cell, and they're guaranteed to be there. So what am I gonna do? Well, I know that these four can form a quad, and I use quad loosely because it's not necessarily coplanar, but you know, it's a quad quotation mark. And I can triangulate it this way. Why? Why can I do this? Well, I've already stored all of my indices before. The way that I do it in my own implementation is I have a hash map that maps the discrete coordinates of a cell to the vertex that has been stored inside of it, such that I can test whether a cell actually contains a vertex or not, just for sanity checking. And I can also find relatively easily the actual vertex that I want to look at. So I know the 4 cells, and because I know the 4 cells, that map gives me the 4 points. And more importantly, gives me the indices of the 4 points. So when I am making my index array, all that I need to do is, okay, so these 3 are going to be connected, and these 3 are going to be connected. Call it a day, and move on to the next edge. Once you do this for every edge, you will actually get a watertight mesh that represents your implicit surface. Now, you should get a watertight mesh. You saw in the prior implementation, artifacts can ensue when the resolution of the mesh doesn't quite match like little details that are inside of the implicit volume, or if you have numerical issues. But roughly in general, you're going to get a watertight mesh, and simpler meshes tend to perform a little bit better. So that has given you your mesh in general, and you're essentially done. There is one last caveat, and I want to return to the last thing that I talked about, which is when you have this diagram, and that is, remember that I said that when you are triangulating, you do like this little quad over here, and then you just do it here, and you do a certain order. You need to test. Sorry, I got something weird on my machine, so I had to cut it. So you are going to assume that your edges are meant to be oriented on the same order as your axis, and that means things should always go from negative to positive. So when you're looking at that edge is going to be axis aligned. So let's say that this is my axis and this is my edge. Now there is a difference in between the edge being negative, in this case black is negative, white is positive. There is a difference in between my edge going from from positive to negative versus it being negative to positive. So these two are a little bit different. Now if you were to look at the little triangle that is going to appear around that edge, if you want to have a consistent winding order, that is to say you want the triangles to always be counterclockwise or always be clockwise, you need to take into account this difference in sign. So if you are in this one, for example, what you are going to do is you are going to triangulate it in one order, and if you're in this case, you're going to triangulate it in the opposite order. That is the end of it in terms of guaranteeing a winding order. So it's not that complicated. In code, it's a little bit funky if you want a very optimized version of it, but that is the general idea. So before I leave, I'm going to show you one last thing. If you found that the prior explanation isn't perfect, or you want a little bit more detail, maybe you want a little bit more math, you want better diagrams than the ones that are hand-drawn, the documentation in NeverEngine has not necessarily in-depth, but it has an alternative explanation of dual contouring. It's a little bit more visual perhaps because the diagrams actually have colors, and there's more math included into it. And if this is not enough, as always, the implementation for the first diagram that I showed is inside of NeverEngine, so you can go and look at the source code. I will link the documentation because the documentation is less likely to change than the code, because it's fairly general and it's describing the algorithm rather than the actual implementation. But you can find the dual contouring implementation as well. Thank you very much for watching, and have a nice day.